Example M6.1, a compound shaft consists of a solid aluminum segment 1 and a hollow steel segment 2. Segment 1 is a solid 1.625 inch diameter aluminum shaft with an allowable shear stress of 6,000 psi and a shear modulus G of 4 times 10 to the 6 psi. Segment 2 is a hollow steel shaft with an outside diameter of 1.25 inch, a wall thickness of 0.125 inch, an allowable shear stress of 9,000 psi, and a shear modulus of 11 times 10 to the 6 psi. In addition to the allowable shear stresses, specifications require that the rotational angle at the free end of the shaft must not exceed 2 degrees. Now, determine the magnitude of the largest torque T that may be applied to the compound shaft at C. So, first, let's recognize that this is basically parallel to your axial deformations, right? When you're dealing with a compound axial member. Only that when dealing with the axial deformations, we're concerned with the axial deformation, the normal stress, and the displacement. While when we're dealing with the torsion, we're dealing with the angle of rotation, with the angle of twist, the shear stress, and the angle of rotation at specific points. All right. So, to make the problem solving process systemic, the following steps will be carried out. All right. So we will draw out the free body diagram by passing sections through segments 2 and segments 1 to expose the internal torques in order for us to apply the equilibrium condition so that we can relate the applied torque to the internal torque in segments 1 and segments 2. Next, we will be solving for the value of T using the allowable shear stress in segments 1 and segments 2, which will yield two values of T. After which, solve for the value of T using the allowable angle of twist. Alright? So, the allowable rotational angle rather. This is not angle of twist. This is supposed to be rotation angle. Alright, so that will yield yet another value for T. And then after that, we will choose the suitable value of T. So, let's go ahead and solve for and start with step 1. All right. So, we pass a section through segment 2, and we find that the T is just equal to T2, or the applied torque will be equal to the internal torque in segment 2. All right. Now, by summing up moments about the x-axis, we see that the torque is positive, the applied torque is positive, while the internal torque is negative. And why is that so? Because we assume that the internal torque will curl towards the will oppose the applied torque rather. Okay, since the applied torque is going in this direction, it is rotating in this direction, it is therefore positive. Why? Because by the right hand rule, remember that if this is your thumb pointing in this direction, your right hand or the other fingers of your right hand will curl towards this direction. Okay, so if your moment is rotating in this direction, then this moment or this torque will be in turn positive. All right, now since T2 is going in the other direction, it is negative, and therefore we have we figured out that T, or the applied torque, will just be equal to the internal torque. All right, and the same thing goes for segment 1. So we know, therefore, that the internal torque in both segments of the shaft is equal to the external torque applied at C. So having done step 1, we can then solve for the value of T using the allowable shear stresses. Okay, and we do that by utilizing equation M6-4. All right. So for member 1, we will have T allow, which is basically our T max, or not T, tau. All right. Our tau allowable, which is basically just equal to our maximum shear stress, is equal to TC over J, where C is the distance from the longitudinal axis to the extrememost fiber of your cross-sectional area. All right. So if this is your cross-sectional area, it's from here to here. Okay, C. So for member 1, we know that it's a solid diameter aluminum shaft. It's a solid aluminum shaft with a 1.625 inch diameter. The distance from the center towards the extrememost fiber is the radius of that shaft, which is 1.625 over 2. All right. Its allowable shear stress is 6,000 psi, and the calculation of the polar moment of inertia is as shown here. And so we calculate a value of 5,055.2 pound-inch for dt. And the same goes for member 2. Now, recall that member 2 is a hollow steel section. Alright? So, if you is a hollow steel section, right? It's written here with a wall thickness of 0.125 and an outside diameter of 1.25. So, what do we notice from the equation? We see that the only thing that changed is the calculation of the polar moment of inertia. All right, since we have to subtract the inner hollow area. All right. However, the C will remain the same. And why is that so? Because again, C is just the distance from, or if this is your equation M6-3, that is tau is equal to T rho over J, where rho is the distance from the center of the cross-sectional area to the point on the area, right? So, being a hollow section will not, being that this is a hollow section, say that this yellow part is the hollow part, and this blue part is the cross-sectional area of the pipe, that will not affect the value for C. That will return a maximum shear stress. Alright? So, substituting values, we have a T of 2,037.7 pound-inch. Now, we cannot possibly determine the maximum value of T from these two values only. Why? Because again, there is a limitation here that says the rotation angle at the free end must not exceed 2 degrees. Now, what is the difference between the angle of rotation and the angle of twist? The angle of twist is the angular deformation in the segment, while the rotation angle is unique to a specified point along the compound axial member. All right, or for example, at B or at C. Okay, now 2 degrees is the rotational angle at C. Okay, so we know that for the rotational angle to be 2 degrees here, it is just the sum of the angles of twist in segments 1 and segments 2. And so, carrying out step 3, we have the angles of twist of segments 1 and segments 2 to be TL over GJ, right? Respectively for 1 and 2. And the rotation angle at C is the sum of these two angles of twist. And since T1 is just equal to T2, which is equal to T, you can factor that out here in this equation. So, Solving for the internal torque, given already that we know the rotation angle at C and all these other variables here, the values for all these other variables, you can solve for T. Also, you should always remember that when applying this formula, you should always convert your degrees to radians, since the derivation of the formula called for the use of radians, and if you use your degrees, you may overshoot or underestimate the value for T. So we have solved for a value of T of 1593.6 pound-inch. Now, given these three values, 1,500, 5,000, and 2,000, which one are we going to choose? Now, this value of T, determined from a limitation of 2 degrees of a rotation angle at C. If I exceed this, will my rotation angle at C exceed 2 degrees? The answer is yes. So, if I choose a value of T that is larger than this, then I will fail in my design consideration, where the rotation angle at C should not exceed 2 degrees, right? And so I should choose something that is lower than this or equal to this. Now, by the looks of it, this is bigger than 1,500, and this is bigger than 1,500. And therefore, the smallest calculated value is chosen, which is T equals 1593.6 pound-inch.